We can get. All right, welcome and thank you everybody for joining us online today for C2 Smarter's webinar. I'm Lizzie, a research project manager at C2 Smarter, which is a US DOT Tier 1 University Transportation Research Center. Today we are joined by NYU Shanghai Professor Xiaonan Wang, who will present Spatio-temporal adaptive AI for urban mobility modeling. Dr. Wang joined NYU Shanghai this fall as an assistant professor jointly appointed by Urban Studies and Computer Science. He received his PhD in 2022 from the University of Tokyo and completed his postdoctoral research on spatial AI at the University of Illinois Urbana-Champaign. And his research interests lie in the interdisciplinary space between urban and AI, and he's been published in top-tier AI and data science venues. As always, we'll be recording this webinar and uploading it to our YouTube channel and onto our website. And we encourage everybody to ask questions. You can do so by pressing the Q&A button at the bottom of the Zoom window, and then we'll read out your questions at the end of the presentation. And with that, I will hand things over to our presenter to get us started.
Thank you, Lizzie, for the kind introduction. It's my pleasure to be here. Actually, just give me 10 seconds. I need to really. Yep, back. Because our AC will automatically turn off at 10 p.m. So it's yeah. So I actually planned this brief self-introduction kind of at the beginning of my talk, but as Lizzie already introduced, so I usually go with Jonah. It sounds very similar to my first name. Yeah, so I'm just joined NYU Shanghai as an assistant professor here. Today I'm gonna talk about my research, and it's majorly about spatial-temporal adaptive AI for urban mobility modeling. So let me actually just get started briefly about NYU Shanghai in case that you are not that familiar with your little brother in the Oriental. So we are the third degree granting campus within the university, with the university's global network after New York, Abu Dhabi, and Shanghai. So we've already been established for 12 years. So we are a very young, diverse, and international campus, in fact. And we have three major divisions. We call it division because we have a kind of a small scale of the kind of academic activities here. But I'm majorly affiliated with art and science and CSDSE for computer science, data science, and engineering. And we have over 300 faculty members from over 30 countries and also over 2,000 students with a very diverse background of over 70 countries, I believe. So we've already established many research centers, and I'm especially working with as a core faculty member to the urban science as well as our AI and deep learning research centers. So they're Shanghai municipal level. So it's a kind of a well-supported research center here, and we've been focusing on. You can see we have a very cross-cultural, and we are focusing on also interdisciplinary research. And this cross-cultural and interdisciplinary research also reflect in my trajectory of growth. So before joining here as a joint appointment of Urban CS, I was a postdoc doing spatial AI as a Lizzie introduced, and I got my PhD from University of Tokyo, and my academic background is majorly in the geospatial information science. So I've been focusing on some AI research since my PhD study. So I'd actually like to start this talk with AI. because we all know AI these days, it's such a hot subject. So what exactly is AI? It's actually the machine's ability to do tasks that require our human intelligence, right? So we've already seen AI that can play chess with us, that can also generate arts with for us, or even chat with us, right? So generate natural language that makes sense to us. So if we think about the kind of the major ingredient of AI, so no matter what model or what task it performs, it always needs three major ingredients, including data. So huge amount of data. So there are data-driven models, and usually we require big chunk of data to fit into the model for training, right? To get your model work, right, you also need to define your model, which is the algorithm. So how, let's say, how the data will be analyzed within this box or black box. And after get your algorithm set up, data ready, you also need the computing power actually to train your algorithm on the data. So these three major ingredients are the essential part to come up with AI solutions. And I'd like to start with data. So I'm a kind of an urban data scientist, and we've been seeing a lot of different kind of urban data, and human are the major layer of for cities, and we've seen different, let's say, traffic or different mobility, such as the shareback usage data with different structures. And this kind of mobility data usually demonstrate very dynamic and complex characteristics. And also they are growing at a fascinating speed. And my research question actually combines with AI, we call it AI definition. My research question actually broadly defines as how we can actually leverage data to understand and make decisions that require human intelligence. So this actually it can be described with a more fundamental problem for this kind of urban data. So essentially we have an urban space, right? It's a two, let's say we take a two-dimensional space, and we usually have some sensors over the space, which comes with geographic coordinates. And on each sensor, we'll get some observations over time, right? This is a kind of very general representation of the urban data we can get. So the problem, a fundamental problem would be, let's say we have some historical observations, right? And the first step would be understand the historical data. So which is, let's say we need to analyze, no matter using what type of the machine learning model, we need to kind of understand such data to find the intrinsic patterns within it, and then make predictions which informs the decision-making process. And here I draw the kind of a temporal prediction problem, but it can also be in other dimensions, let's say over space or within like interpolation. So there can be different modeling tasks, but here it's just let's take the prediction as a classic task. So to perform such data modeling task over this space and time, what people usually do, let's say a statistician or data scientist, usually we would assume some underlying assumptions. right? Here, the assumption over the time and space would be autocorrelations. So let's say over the space, we would consider the spatial autocorrelation that related to the distance between the sensors. And over time, we'll consider, let's say we use time series model that would have the underlying assumption of stationarity, that the statistical property of the time series does not change over time. That means stationary, right? But do these assumptions really hold in the real world? The short answer would be no. Let's take a look at both dimensions. So the first, over the space, we will have heterogeneity. So spatial heterogeneity is a standing out characteristics in many geospatial data. So let's take this road network as an example. In a road network, we would have many different types of roads. So we will have local road, we have highways, interchange between them, and they would demonstrate different kind of dynamics and also different value skills in terms of the, let's say, traffic speed, if we measure the road chunk and travel speed. And we can see that highway demonstrates this very typical traffic pattern with a rush hour after work, rush hour kind of a drop. But on the comparison, the interchange will have let's say, more uniform but lower traffic speed on average compared to the highway, which is a very straightforward observation. But over the space in the network, right, they are intertwined with each other. So it's not necessarily a basic spatial assumption or autocorrelation assumption. So how do we deal with this? This is a first challenge. And the other ones over the time. Over time, let's say now we are interested in the citywide dynamics over the traffic network. And we plot out all the sensors time series together so that now we have this time series histogram chart. So the lighter the color, the more points you have at each corresponding time and the traffic flows of a road chunk or a road sensor. And we can see that over time, there will be some different kind of external events. In the previous case, actually, I also showed the traffic incidence case. It's gonna cause a local abnormal behavior of the traffic. But in this case, we consider let's say we consider citywide event. No matter a holiday, such as Christmas Eve, New Year Eve, there would always be some kind of anomalous pattern. For example, people would not go out on Christmas Eve, or people would go out on New Year's Eve to celebrate and then go back home. But we can also notice there's a very anomalous case, which is caused by some, let's say, extreme weather or even COVID lockdown, so that nobody would go out at all. And this actually disobeys the kind of a periodic pattern we would expect, right? So under such event scenarios, the predictability, if we model the data, would drop a lot. If we use, let's say, we have a trained model that models the periodicity, but here events come, so that it would make a lot of prediction errors under such scenario. So this is known as a temporal non-stationarity. No matter we consider the spatial heterogeneity or non-stationarity, they always raise some exceptions to the underlying assumption for the modeling task. So that's the nature of the real world data. You will always get such anomalous patterns that's not as expected, right? So that's about that's the urban data challenge I actually quickly summarized. And my research actually been focusing on developing some adaptive AI algorithms to no matter mitigate or resolve this problem to some extent. Let's see how it works out. So I'll break it down into majorly two parts, the spatial adaptive AI and also temporal adaptive AI. So from the algorithm perspective. So firstly, so this is a backbone of my research. I used majorly graph neural networks, or known as a GNN, to handle as a basic unit to handle spatial dependency. By spatial dependency, that means, let's say we consider traffic signal and adjacent nodes, adjacent roads, there will be some diffusion process. Let's say if there's a traffic accident happen somewhere, and the congestion would diffuse over the edge of this network, right? So formally, the definition of such network, we denote that with graph topology, and it's a set of vertex or node that represent, let's see, each end of a road, and we also have edge. So how the nodes are connected, right? And also for the edge, let's say there are in total m nodes, so that there's a weight matrix we can use to describe how those nodes are connected, how strongly they're connected or related to each other. So this weight matrix or adjacency matrix, it's a very important definition for graph neural networks. And we, at the same time, will have some graph signal. Graph signal is basically, let's say we take a certain time step and we will observe p variables on each node, right? So let's say we have a traffic speed, traffic flow, volume, occupancy. So there can be many different variables we measure on each sensor. So this is a traffic signal. And the graph neural network is basically formulated as this equation. We essentially need the weight matrix as an input as well as a graph signal. It will learn a hidden representation of the input signal, graph signal. So you can see that this Q, the hidden variable Q will be a hidden we call it a embedding dimension, so that it's a kind of a latent space variable for the graph signal. So given the graph kernel, this parameter matrix, that's a general GNN definition we adopt. So essentially, you can see K here, it's a approximation order that's originally derived as using the Chebyshev polynomial equation. And basically, it denotes how many steps the graph signal can diffuse over the edges. So this is a basic unit. We handle the traffic signal diffusion on the graph over this weight matrix, right? So because the graph signal, it's the observation, basically the historical data that come by given, right? But we need to consider how this weight matrix is gonna be defined. Simply, let's say if two roads are connected, their they're denoted as 1, otherwise 0. And at the same time, we also need to consider how far they're located, right? So in this case, there are some underlying assumption coming with a GNN if we use that to model road networks. So there's actually a first law of geography, which is a very empirical law that states closer things are more related than remote things. So you can see it's an empirical statement. So essentially, let's say we have this set of sensor over the space. If we want to measure a pairwise relationship, so basically that's a single element in the weight matrix. And based on the first law of geography, we will consider to consider the distance factor into this weight construction as well, so that if they are closer, essentially we define this Gaussian matrix. If two nodes are closer, so it's inversely related to the distance, right? So if they're closer, they're stronger related. Otherwise, they're weakly related. If, let's say, the distance go over a certain threshold, we would consider they are not related anymore. For example, this node, because we need to have a sparse graph representation. So that's a first thing, considering the distance factor into the graph construction. Also, there's another underlying assumption with the GAN, which is known as a homophilic assumption. Homophilic assumption, that means adjacent nodes are similar. So if, let's say, you bring these two nodes connected, there's a edge, such an edge. That means they are similar. But in fact, it's not the truth in the road network, right? Because as I demonstrated, let's say, highway interchange local roads, they can be intertwined and connected to each other. So we need to do something with the graph neural network if we want to apply that to road network, to model road network. So here it's I would consider a motivation that I initially thought from there was another third law called third law of geography that considers a spatial prediction problem. Basically, it's about the similarity metric. It's not going to be simply based on the distance. So it's not necessarily closer things are more related. Now we want to consider another set of so-called geographic configuration. A straightforward example would be if you want to consider how similar, let's say, two neighborhoods are, how in terms of their safety, you want to consider their demographic, social economic factors, and those are known as geographic configuration. They come with each, no matter census tract or the other spatial unit you consider. And if such configuration are similar, so this similarity metric, if they are similar in this variable space, latent variable space, no matter what set of variable you consider, you can calculate any, let's say, cosine similarity of that, so that they would also be considered as similar in the physical space. So it's not bounded, strictly bounded by the distance anymore, right? So this is actually something I originally thought from. That's because the road network is not necessarily bound the similarity. Let's say the types of roads, there should be some other ways we can illustrate the types for the traffic modeling task. So here it's the technique actually from the AI models perspective, which is known as memory augmented neural networks, which was originally designed in computer vision research for detecting anomalies in the computer vision tasks. So the core idea is that to bring a extra set of parameters, in this case, a parameter matrix with a dimension m by d, which stands for m vectors, a set of m vectors, and each vector has a dimension of d. And the idea is to use this parameter matrix to mimic the geographic configuration. So they as a variable, but instead of arbitrarily choosing, because in the previous case, let's say we need to choose, you need to decide, people need to do some feature engineering. That means you need to decide which feature, let's say demographic, that's related or not related to a certain task. But now we don't have such kind of empirical practice. Instead, we want to parameterize. So we want the model find such pattern by itself. So that's a reason why we have such set of parameters. So memory vectors or memory items, we will call it. In this case, if we have such a set of vectors that are well selected or well trained, then it's gonna be able to use different combinations or a different subset of the memory vector to represent the different types, or that you use different sets of the vectors. That means it's like our brain, right? We use different part of our memory or brain to do different things. That's a kind of essential idea here, that we want use this to distinguish different types of sensors or nodes in graph. So how we achieve this, it's based on we encode the different temporal dynamics. So previously I illustrate, let's say we have an intertwined heterogeneous road network, but different types of roads would demonstrate different dynamics, such as a highway or interchange local roads. And we can use some kind of a recurrent neural network or neural networks that handle sequence data. We encode such sequence data, right? So that the difference of the nodes can be represented and finally embedded, encoded into the memory network, so that we can use the different sets to illustrate the heterogeneity. So that's the idea. And this work is majorly implemented in this triple AI paper. So this is a joint research with Toyota when we were in Tokyo. So we used a lot of Toyota's vehicle trajectory along the roads. So specifically on the expressway in Tokyo. So here it's a road network, the major expressways in Tokyo, and each road segment we consider as a node. And we finally come down to this 1800 road segments. And they're composed of different types of roads, including the expressways interchange. And it was a 3 months data and a 10 minutes interval for the time series for the signals. And we can see if we randomly sample 8 sensors out of this road network. So there are different dynamics if you can tell the value range and also the shape of the time series. So there are different types of nodes, and we want to have a model that can predict, let's say, the different types of roads at once, right? Because that's how the GNN works. You have this graph signal, you have a sequence of graph signal. So let's check out the performance. So I skipped the numerical comparison part, only show some interesting results. If you're interested, you can always look into the paper for the technical details. But because we proposed, the idea of this is to illustrate how the heterogeneity can be distinguished by the memory network. So we break down this disentanglement from different dimensions. So firstly, let's check out this spatial disentanglement. By spatial disentanglement, I mean because the road networks, they are intertwined with each other, different types of roads, right? It's not necessarily, this part is I think it's intuitive that we want to, let's say, make the prediction at the same time we want to understand how or where those different types of roads are located, right? So I adopt this cross-K function. Cross-K function is it's a spatial index, spatial metric that we use in geospatial research to measure how two types of spatial points are located or clustered with each other. So in this case, with the road network data, we take toll gates as a ground truth. We want to compare how the different types of roads are located with toll gates. So this is a first case, actually the highway road segments. And this black dotted line denotes a random distribution of these two types of nodes. If in this case, the first cluster, which is a highway in blue, they are under the dotted black curve. That means it's now significantly spatially related, clustered with the toll gate. But in comparison, if we consider the other cluster, in cluster 2, which illustrates actually the interchange road chunk, and it's a curve in red, it's much above the random distribution of the black dotted line. So this is how although different types of roads, they are interconnected in the road network altogether, right? If we simply we encode the temporal dynamics, and we can directly distinguish where they're located. At the same time, we make prediction. So based on the memory network. Without that, the nodes are going to be considered equivalent in similarly treated by the graph neural network in the prediction model. So that's from the spatial perspective, how the different types of roads are distinguished. And if we take a look at the temporal dynamic, so now we want to illustrate the daily average of these two clusters. The first cluster are the highway road segments, and the other is so in blue that's the highways, but red are the interchange of the expressway. And in this case, we print out the time series histogram of these two types of roads. And we can see that they're clearly different from each other in terms of the shape, right? So the highway in blue demonstrates a very typical daily traffic pattern with the morning and also daytime after work drop of during rush hours. But at the interchange road segments, the traffic speeds, this chart, it's very noisy because there are a lot of accelerating and decelerating process and the targets towards the targets, right, on the interchange. So this is an illustration of how because we encode the temporal dynamics, so that's how they are reflected and the daily perspective. And the most important dimension we are going to check out, it's from the memory, because the assumption was that we want to use different part of this memory to distinguish such heterogeneous roads, right? Now we print out the weekend time series. So average on the weekend, because the pattern here is standing out. So this is a Friday, Saturday, and Sundays, how the memory are queried, are checked over, are used over time, over the weekend on average, right? So we can clearly see that for the highway node, for the highway roads, the model always checks the memory vector 0 and memory vector 9, because it's so the lighter the color, the higher weight. But on the contrary, for the interchange, it always checks the memory vector 2 and 7. So they are mutually exclusive from each other. So basically, the memory would use vector 0 and 9 to represent highway dynamics, but use vector 2 and 7 to represent interchange for how the traffic changed over time, right? So this is a kind of how the heterogeneity come down to the different part of this memory. So I would like to take a pause here. Oh, actually, this is a first section for the spatially adaptive AI. Essentially, we use a memory augmented neural network that are trained to distinguish spatial heterogeneity that can now be achieved with an empirical, let's say, distance-based or similarity-based metric. So it's the first algorithm we come up with, and the second one actually it's about temporal adaptive AI algorithm. So let's quickly revisit this problem again. Essentially, it says that we want to model the network level traffic dynamic. And there are always some, no matter external or citywide events, such as holidays or extreme weather. Those are going to cause some anomalous patterns into the traffic. And under such scenario, the predictability drops, and which is known as, we call it a non-stationarity problem. And so to solve this problem, let's firstly talk about how we model this dynamic process with a graph neural network embedded. So let's say here it's a urban space, we have some traffic sensors. And the first thing we need to do, so the spatial function essentially denotes a graph neural network. We need to consider how the graph topology are connected, or the edges are connected, and how their weights are, right? How strongly they're connected. At the same time, we also have the observations, which is the graph signal or traffic signal over time, right? And we perform the graph neural network, which allows the traffic signal diffuse over the edges. And we have a sequence of the graph signal. And how we're gonna deal with the dynamics would be based on this temporal function, which calls this graph neural network recursively, so that at the same time the graph signal can diffuse on the edges. It also evolves over time, and then we use this model, this spatial-temporal function, to further make predictions for the future based on the historical observation. So that's the underlying algorithm. I want to highlight one thing, because if we pay attention to this parameter, the graph kernel within the graph neural network, we can see that we always use the same graph neural network across time, over time steps, which means this parameter setting is static over time. It's time invariant, right? So if we consider this, the model mechanism to the data scenario, if let's say we have a normal pattern, traffic pattern, the model, the parameter would be trained to fit those, because most of the historical data, most of the case, you would expect to get such normal pattern, traffic pattern. So that we mean by the static parameter only fits the general pattern. So that works for most of the case. But you are gonna get some anomalous pattern that if you take the historical data and makes a prediction, that's gonna fail at all. So because the predictability problem by the event. So that we need to do something with this parameter setting. If we can make the graph neural network parameter adaptive over time, that means we can solve this problem. So that's a motivation actually for this AAAI 2022's paper. So essentially, the technical design would be, let's say we have this sliding window, and so we take the traffic stream as a real-time input, right? And with we have some kind of the encoder, the model I just mentioned, the spatial-temporal function. And we have a similar structured memory bank. But in previous case, we encode the spatial nodes, but here we encode the dynamics as well, so that each memory vector would represent a typical traffic pattern. So this periodicity, you would see later on, it's gonna be decomposed into some wavelets of this time series histogram. And how it works, it's gonna be after the encoded representation we get from the graph, a sequence of graph signals, we're gonna use that to match with a normal pattern and find similarity, whether it can be represented by a existing set of the memory vectors or not. If it can be represented, that means it's a so it's similar at least somehow to the existing historical data. That means that's a normal case. But if it's not, then it's an anomaly case. That means we need to update the parameter. So this is a design for such event detection, similarly to the anomaly detection task. At the same time, we use a hypernetwork. Hypernetwork is a meta-learning technique which generates or updates the parameter based on another neural network, so that we can do this update in a on-the-fly fashion throughout the time sliding window. So it's gonna be able to handle some extreme case. You're gonna see the case studies later on, but here are the data sets we use for measuring such temporal adaptive AI, so that there are two human mobility data adopted from US, one from the NYC open data set. And in this case, we consider the different mobility modes, including the taxi and shareback data, open data, and we measure their travel demand and supply in each grid. And we consider the holiday season, basically end of year in 2015 and at the beginning of 2016, there was a historical winter storm called Blizzard Jonas, and which caused some anomalous travel behavior at that time. And the other data set we use is a COVID lockdown data set, which will measure the point of interest visit of 10 categories over the first wave. So in the middle of 2020, that was the most severe period of time for COVID lockdown for US. And we're gonna see how the adaptive AI could handle such anomalous event scenarios. So here it's the tour. So the prediction task for the NYC Jonas case for the taxi demand. Here it's a ground truth. We can see during the blizzard, there was roughly no traffic at all during this event day, right? And the demand gradually recovers after that. But the state-of-art prediction model, when this work was done, was only able to make very naive prediction. By naive prediction, I mean by simply repeating the latest observations. That it's the safest kind of a behavior the model can do, right? Because it doesn't know what happened during this event day. But let's check out the adaptive AI solution. Now, given the detection and also parameter adaptation that we can see, the model can gradually adapt to a kind of a zero mobility period and gradually recovers afterwards. And if we further check out how the memories are, because each memory vector represents a normal or traffic pattern, right? So we can see this vector 2 and vector 6, they're acquired somehow differently over this event period. Actually, we make a comparison of this Jonas scenario to a regular long weekend holiday, so Martin Luther King Day, and also if we compare to the regular workday, if we check out the vector 2, it's strongly queried and the kind of a transition of each day. So that's a nighttime pattern. So there was no mobility. So people rarely go out on nighttime, right? So that's also reflect this anomalous pattern because and during the event day, people seldom go out. That's similar to a nighttime pattern. And there's almost no, this is a vector 6 stands for a middle of day. So a active period of time. So there's no go out during this event day. If we check out this decomposition or the wavelet, how this time series components are queried over the event day, we can understand that the model actually decompose such behavior and use that to decide which vector to choose, right? And it's this selection of set is different for this event, extreme event, also for normal workday or the event weekend. They're totally different. So this is a first case study. And the other one is for the COVID lockdown. So we measure the point of interest. There are in total 10 categories. And overall, if we check out the ground truth, this is the end of April to May, which was say right in the middle of the first wave of COVID in 2020. Overall, we plot out this stack plot, and there was a negative trend. The state-of-the-art model, given the normal training data sets, it actually yields an opposite pattern. But we can, based on the adaptive AI's method, we can see it not only captures the overall trend, but also can describe better let's say, the local details for this smaller scale of visit on the event on this Memorial Day, the holiday. And if we check out how the memory vectors are queried over time, it's also surprising because this vector 4 was not even in the picture and the normal situation, right? So for normal days before the COVID came, so that's end of 2019 to beginning of 2020, the mobility pattern was quite regular. They kind of go out and also some holidays here, right? But there was a emerging query of this vector 4, which standing for anomalous, which is an unprecedented pattern that never happened before. And this is how the model actually adapt to learn a new emerging mobility pattern. So it's based on, so the quick takeaway message here is that what the model really does based on the memory network is to decompose the complex signals and match it with normal patterns to find out anomalies. So this is actually the idea underlying such spatial and temporal adaptive AI. So I think I run too long than actually my expectation, but here comes to an end. The computing power, basically another important component to AI model. So essentially, I would like to acknowledge and also give credits to all universities and institute that supported my research. Especially currently, I've been working with our Urban Science and AI Research Center. And in terms of the computational resources and the complexity, because I've been doing this AI research, so I think their support is hugely beneficial for me and also for my future research as well. So this is the end of my talk, and I look forward to collaborating with you, with civil department and the faculty members, and also I want to interact with students here, and I welcome any questions if you have.
Great. Yeah, on that note, if you have a question, please use the Q&A button at the bottom of the Zoom window. And we do have one, which I'll read out. It says, how does the adaptive AI differ from traditional Bayesian approaches?
I think that's a good question. So Bayesian's approach, I think it's so let's say based on the let's say how this, because if we consider the traditional graphical model, that can also be used to, let's say, to handle the transition of the states over time. So that's a kind of a sequence model. People use that a lot to handle, let's say, for example, in this case, a trajectory data, so that we have some kind of a transition matrix. And in that case, you also need to optimize some parameters, no matter, let's say, you use a hidden Markov model to handle that. But in this adaptive AI approach, it's so the memory network more functions like a hyperparameter. So basically, it controls how the models have been learned. are trained in the training process. So if you consider, let's say, a high-level technique that I mostly used throughout these two works I mentioned today, that's a meta learning. So basically, what we are trying to do is that we want to kind of regulate how these parameters in the training process happen, right? So that's why we design such adaptive. We phrase it as adaptive AI, but essentially the core of this implementation is based on this memory augmented neural network.
Okay, great. If you have a question, please feel free to type it in. That's the only one that we have at the moment. So I'll wrap up, but again, please keep them coming if you got it. But thank you everybody for joining and to Dr. Wang for today's webinar. As always, the recording will be available. Oh, we have another question. How much data was used for this?
Oh, that's a good question. So because I think I skipped some details about the data set. So for this traffic network data in Tokyo, that was a 3 months and 10 minutes interval for the almost 2,000 traffic nodes. So essentially that gives us let's say 40,000 data samples, kind of a time series. In rough, I think. And for this, it's all, I believe, more or less at that level. And in terms of the data sets, because we have a high dimensional, because involves spatial and temporal dimensions. So over the time, it's gonna be decided by how many days or what's the time interval we use, right? But over the space, it's also important because this depends on how large our graph is, right? For example, if I have a very large road network, a complex one, because we also simplifies into the highway expressway. But in case I believe the existing graph neural networks, I think from the engineering perspective, there are still some room for improvement if you want to implement the sparse representation, sparse matrix multiplication that can handle even very larger scale data on road networks. Yeah, I think, yeah, I kind of extend the topic a bit, but in terms of the data sets, yeah, I think overall, usually for such traffic prediction or this analytic task, several kind of 10, 30, 50,000 of data samples of time series are common, I believe.
Great. And then we have one more, which is more of a comment, which just says, thank you for the fantastic talk, which is essentially what I was going to say. So just to wrap it up,
Thank you,
it's
Lizzie.
almost,
Thank you very
it's almost
much.
11 on the dot. I believe I was saying that the recording will be available on our YouTube channel and website. And as always, the webinar was brought to you by C2 Smarter and the USDOT's University Transportation Center program. Thank you, everybody.